So this begins on page 596. Okay, so let's start with the idea of a sequence. So a simple verbal suggestion to how to think about it is that a sequence is a list of numbers, and you are considering the list of all the numbers in its entirety almost like a set of objects. But instead of just being a set of numbers where the order doesn't matter, the order does matter. And so you list them from the first to the second to the third term. So an example of a sequence is I could use the old set notation, which you may recall as those curly brackets. And then I could list the numbers, giving the first one first, etc. So I'm going to say, let's say we had a 3, and then they're usually separated by comma when you have set notation, and then maybe a 5 and a 7 and a 9. So as I'm listing out the values of a sequence, there's two possibilities. That there's a finite sequence, meaning there's a finite number of numbers in my sequence, or that it's infinite and that it just keeps going and going and going the same way that it started. So if I, for example, close my notation here, then this is called a finite sequence. And in this case, it just has 4 things in it. But right beside it, I could write that I have the same 4 values in my sequence. And then instead of having it end on a 9, don't like my 9, instead of having the last term of the sequence be 9, if I put like a dot, 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 that would suggest that the sequence keeps going infinitely and that it follows a hopefully recognizable pattern. So then this would be an infinite sequence. And it's still the ordered collection of these numbers that we're talking about. So I could try to describe my infinite sequence here verbally, like I could say all positive odd numbers starting after a 1, starting with 3 and then continuing on up from there. So that's sort of a way you could try to describe it. Maybe by simply looking at the values you see, you could see the pattern to try to predict where the sequence is going and what the rest of the terms would be. But that's not necessarily a given. Kind of depends on how complicated it is and whether it feels uncomfortable to figure that out or not. Questions so far? Okay, so in order to work with these things, pretty quickly we need to introduce some notation. So the definition of a sequence, which I won't write in its entirety, but just reference it, is on page 597. And they basically say that for a sequence, we're going to use the set notation. And then in general, when we don't know what the numbers are or what even some of them are, we're going to write inside an A or a B or a C, the kind of letter we would typically use for a constant. And then we're going to write the subscript n and then box it up in a set notation again. So I would refer to this as the sequence of A sub n's. And the subscript, the n, is telling you which number on the list you are referring to. So for example, in the sequence that I have above here, let's say I go up here, I could write that A sub 1 was equal to 3, and A sub 2 was equal to 5, because 5 is the second number in the list. Well, again, it's an ordered list of numbers, and so the little subscript of n in this notation refers to which position at the list you're particularly looking at when you put in a particular value like 1 or 2 or whatever. So we can literally think of, if we were to write this out, as I did in the example above, that the first one we'd call a sub 1, then the next one we'd call a sub 2, a sub 3, etc. Questions about that? All right, so this is the notation we use. We use a little subscript on an A, and if we put in a particular value for the subscript, then we are referring to one of the numbers on the list in the sequence. The nth term of the sequence, the third, the fourth, the fifth. And if you have example given, you may be able to actually figure out what that is, and that's what some of our early problems start with, just getting used to this notation. Let's do that. So let's look at a specific example. So this is the book's example 1, page 597. So it says, here's some explicit formulas, and I'm going to look at their number. Well, let's start with A. So for their example 1A, it says that A sub n can be determined by plugging n into the formula, or 1 over 2 to the n. So this is referred to as an explicit formula because instead of giving you a sense of what's in the sequence, as I did up here, by actually listing out some values, they give you a formula that you would use to determine the nth value in the sequence. Yes, question. Sorry, was there a question there or no? Hello, someone speaking up there? No? Okay, so what do they ask us to do here? It says use the explicit formula to write the first 4 terms of the sequence, and maybe even sketch a graph, which they do for you in a nice picture, which I'm not going to try to do. Okay, so that means they want us to figure out a sub 1, 2, 3, and 4. So to figure out a sub 1, we would literally insert a 1 into the formula given for n, since n is a 1, and that would be 1 over 2 to the 1, which is 1/2. So for a sub 2, n would be a 2, so we'd have 1 divided by 2 to the 2nd power, which would be 1/4, etc. So a sub 3 would be 1 over 2 cubed, which is 8. And a sub 4 would be 1 over 2 to the 4th, which is a 16. So in this example, we are given a formula which explicitly allows us to calculate the nth term of a sequence, and then we could use that formula to write out some of the terms if it hadn't been given to us that way. And a lot of times this is really helpful to just visualize, because if you just see this formula, it's less clear than actually seeing like a sequence with numbers in a box or something like that. Questions, comments, discussion so far? All right, so if we look at example B, let's get to the color that I want. So they give us a formula in B, which is a sub n, and then I'll give you guys a minute or two to see if you could write the first 4 terms of the sequence yourself. And so in the formula, in case you don't have the book with you, is a little bit more complicated. So it's like this. It's got a -1 raised to the power of n, and then that's times an n, and that's all in a fraction divided by n squared plus 1. So think about it, give this a try, but here's what you're trying to do. You're trying to figure out what is n sub 1, what is n sub 2, what is n sub 3, and what is n sub 4. So yeah, I'll take a minute just to let you guys try that out. So is someone able to come up with a sub 1?
Negative 1/2.
Negative 1/2. Anybody get something different than that or have a question about how that's obtained? So basically you're imagining when n is a 1, you would put in a 1 here, and here, and here, and then follow PEMDAS and get negative 1/2. Okay. So how about when n is a 2?
I think 2/3. Dang, it was really quick.
2/3 is pretty close. I think you forgot to square the 2 on the bottom.
Oh yeah, 2/5.
Nice. There we go. Good adjustment. So what I'm doing is I'm putting, this is a negative 1/2. This is 2/5. And as we're figuring these out, I'm putting them down as if I was writing a sequence term by term. Okay, and somebody new want to chime in if they were able to get a sub 3?
Negative 3/10.
Negative 3/10. Anybody disagree? Okay, and one more person if somebody can get a sub 4.
4/17.
4/17. Trust in you guys. So if they give us a formula, it's kind of nice because you can just go directly to any term in the sequence that you want. So imagine if I write out the sequence as I have here, because we figured out the first 4 terms. If you were given the sequence as I've written it here, imagine how it might be more challenging to understand what the sequence is. Like, could you predict what the next term would be if you didn't have a formula to tell you? Maybe you could. Maybe, for example, you could see that the top is just 1, 2, 3, 4. So it's just going up with the number, and that it's alternating in sign, -1, +2, -3, +4. So you might be able to predict that the next one is probably -5. But on the bottom, it might be hard to see that it's 1 more than the square of the position of the number. That might be hard to see as just pattern recognition, right? So that compare a sequence provided to you in a formula format compared to when it's provided to you sort of written out with the first few terms and then relying on you to see what the pattern is on how to extend that if you needed to. Questions, comments, discussions about that? Okay, so again, just to start to help with some terminology, these, both of these and examples A and B are infinite sequences because you can extend the values on indefinitely. As n gets bigger and bigger and bigger, you keep producing new numbers and you get this infinitely long list of values. One of the nicest ways to provide an infinite sequence is with a formula, as these 2 examples did, because if you have a formula, you basically completely explicitly know every term of the sequence just by plugging in the nth value that you want to look at and seeing what you get. A harder way to see a sequence is when it shows up just as a pattern of numbers, 3, 5, 7, 9. And in some cases, it may not be that much harder, But even if you have the 3, 5, 7, 9, it might take you a little while if I asked you to say, well, what's the 150th number in the sequence? Whereas if you have a formula for the sequence, you just plug 150 in for n, and then you can immediately directly go to what the 150th value on the list would be. Questions, comments, discussions about that? Okay, so next concept up. Let's see if we can ride down this table a little bit. Is now, let's say we have a sequence. We want to consider the limit of a sequence. So if we have, well, let's introduce it this way. So we might want to consider what is the limit as n tends to infinity of a sub n. So a sub n is my notation that refers to the nth element of a sequence. And as n gets bigger and bigger, you proceed down the terms of the sequence, then you can ask if that sequence itself has a limit, meaning does it approach infinitely close to a particular number as n goes off to infinity, as you go further and further down the list. And so this ends up becoming a limit problem, and this takes us back to chapter 2. So we're going to start to use some chapter 2, I'll say skills or previously learned stuff. Excuse me. In trying to determine whether a sequence has a particular limit. So consider the example that we were just looking at. 1 over 2 to the n was our formula for this one here. Yeah, let's look at this, this one here. A sub n equals 1 over 2 to the n. So if that was my value of a sub n, then I would be saying, is there a limit as n goes to infinity of 1 over 2 to the n? So how do you guys feel about that? When you look at that limit, does that feel comfortable? Do you feel you could evaluate it? Do you say, I don't know what to do with that? Can we get a little feedback here from folks?
Yeah, actually, I had a question about the explicit formula, the negative 1 to the n times n over n squared plus 1.
Yes, sir.
So that's for any sequence. That is the formula to figure out a sub n.
Oh, I'm sorry. No, that was an example in which it gave us a specific sequence. Yes,
You could figure it out.
that's right. So for example, in A, the formula is 1 over 2 to the n.
Right.
And so that's a sequence different than the one in B.
So if we went up to the top where you had the example of a infinite sequence and a finite sequence,
Yes.
you could say that the formula for that is basically just every odd number.
Well, that's not a formula, that's a description. So let's say we wanted to do a formula just to put our minds behind this. So here, for example, in both of these, I'll just give you a formula, a sub n. So how can I get these odd numbers using n as a value? Well, just to save us time, it's 2n plus 1.
Cool.
Does that make sense? So, yeah, so it's nice. So in this case, for the first one, n goes, oh, this is not working nicely. N goes from 1 to 4 because we only had 4 terms in the sequence. Whereas in the second sequence, n goes from 1 to infinity. So in this case, I could say we have, I'm going to give you some notation just to see how it works for you, where I have the sequence of 2n plus 1, where n equals 1 to infinity. So the book uses this notation that I've just drawn on here, and I think they have examples of it on page 599. So notation on page 599, in which you use this set bracket notation that I've been showing you. And instead of putting like a sub n in the middle, as we did down here under the definition, you literally put the formula for a sub n inside the brackets, as I've done here. And then if it was a finite sequence, you could literally give how many terms there are by letting n go from 1 to 4 or 7 or however many terms there are. Or if you have an infinite sequence, then you can put an infinity on the top, just almost like an improper integral kind of a notation. And then this ends up being the sequence defined by 2n plus 1 as n goes from 1 to infinity, is a way of describing this notation, which then describes this infinite sequence that I gave in a first example. How do you, you feel okay about that?
Yeah, that makes sense. So given a sequence or given a formula, we could find either or, basically.
Yeah, we are basically trying to understand the idea of having just this big list of numbers that often will be infinite, and more difficultly, warming up to all the different notations to try to talk about it and write about it.
Okay, cool. Thank you.
And so an explicit formula is nice, because then you know every term of the sequence by just plugging in whichever term you're interested in. So the formula is a nice format, but it is possible that you don't have a formula. Like I said, out in the real world, you may observe some data values and there's no formula written on a tree somewhere for you. And you have to kind of try to figure out what the formula might be if you need that way of writing it. So then we had multiple examples. So here was one up here where the formula version of it would be 2n plus 1. And then they gave us an example in the book on page 597 where they had one was 1 over 2 to the n, and then another one was this more complicated thing with the minus 1 to the n power, etc. So with these ideas in mind of having an infinite sequence, we then look at this concept of the limit of an infinite sequence. And as an example, I'm having us look at their example 1a sequence that they gave us, 1 over 2n. And so that brings us back to this question. First we want to think about the idea of a sequence having a limit. Again, a limit would be a number, an L, in which the terms of the sequence as n goes to infinity gets arbitrarily close to L, that it zooms in on that value. The official term is that it converges to a number. If the limit exists, then we say that the sequence converges to a value. So how do you guys feel about that? And could you evaluate, if there is one, the limit as n goes to infinity of 1 over 2 to the n?
It seems like it would go to 0.
And that's a nice conclusion. That is correct. So how could we, let's go back to chapter 2. How would we figure that out? How would we investigate that if it wasn't clear? We want to do two things. We want to both remind ourselves of the results of limits that are sort of fairly easy to see, and also remind ourselves of tools that we can use to evaluate limits when they're more challenging. So how could we justify that? Like, what do you see there that allows you to conclude that you think it's going to 0?
That 2 to the infinity is just infinity. 1 over infinity is basically 0.
Okay, so that's it's kind of a nice way to sum it up. It is sound a little bit more arithmetic-ish, and of course we can't do arithmetic with infinities, so there is a comfort in the way you said that, but also a danger. So let's look at this for a second. Okay, so what if I, for example, gave another limit? Consider the limit as n goes to infinity of 2 to the n over 3 to the n. Thoughts, questions, comments, discussion?
Wouldn't, since both the top and the bottom are proportionate, wouldn't that just make them, wouldn't they reduce to 2/3 every time?
So I cannot cancel the ends here. If that's what you're trying to do. So let's explore this by looking at the sequence, because we want to remind ourselves that we do have a sequence here. So let's just say note, or sort of envision. So when n is a 1, we have 2/3, right? What do you get when n is a 2?
Four ninths.
4/9. So a sub 2, the second term in the sequence, is 4/9. And a sub 3, what's the third term?
8/27.
Yep. So the first one there is 2/3, but I would point out that none of the others simplifies to 2/3. So we do have a sequence of values, and I'll put up here that we have 16 or 81, and then I'm going to put dot, dot, dot. Sorry for the interruption. Son, you need to stay downstairs, baby?
I need to find grandma my pen.
It's not up here, honey. Sorry for the interruption, guys. My kids are made to stay home just the way our campus is making the students stay home. So
How old are they?
my son is 11 and my daughter's 9.
That's nice.
Okay, so yeah, so let me put this little bracket in here. All right, so what I'm doing by noting this is reminding us that we are referring to a sequence, and then we have the limit as n tends to infinity of that sequence. So what this is asking us to see if we can determine is if these numbers on this list that goes down infinitely long settle in on a value. So how do you feel about that?
Is it equal to 1?
So like I mentioned before, we had a 0 up here. What's your thought process that allows you to sort of think maybe it might be a 1?
Because 2 to infinity will give you like a huge number, probably an infinity, and infinity divided by infinity gives you 1.
Nice. Okay. So there's so when we were looking up at this example here, let me just remind us when we were looking at this, the descriptive argument was like basically that 1/2 to the infinity is the same as 1/0, which is equal to, I'm sorry, 1/infinity, which is equal to 0. I was getting ahead of myself. And so what I said is there's some simplicity to that that kind of helps you try to draw that conclusion that way. And so the comparative argument over here is that I have an infinity over an infinity, and that gives me a 1. So there was a simplicity here, there's a danger here. So this is not a 1. So let me do a little reminder of some of the limit logic from chapter 2 of how we have to think a little bit deeper to figure these things out. So here's a trio of examples, and then we'll go back to the one we're looking at. So reminder, some examples. If I have the limit as x tends to infinity of x over x, I get 1. If I have the limit as x tends to infinity of x squared over x. Well, that simplifies to the limit as x tends to infinity of x, which is infinity. And additionally, if I have the limit as x tends to infinity of x over x squared, that simplifies to the limit as x tends to infinity of 1 over x. And again, this is an example like our 2 to the n, where the denominator is becoming huge. So I have 1 over 100, 1 over a million, 1 over a billion, and that goes to 0. So I'm showing you this trio of examples, which is like a chapter 2 thought process, to remind us that when you have an infinity over an infinity, we don't know what that equals. Because in each one of these fractions, I had an infinity over infinity. As x goes to infinity, in every one of these, the top and the bottom goes to infinity. So I can't really use this simplification and say that an infinity over infinity gives us 1. It's possible that it might give us 1, but it could give us infinity, and it could even give you 0.
So is that why they call it indeterminate?
Exactly. So this is what we called an indeterminate form. And you may recall that things like that were candidates for either what I did here, which is an algebraic simplification, which then allows you to evaluate the limit. Or possibly you could even do something fancy in this format with like L'Hopital's rule or something like that. So what does that basically tell us or remind us? That limits are harder than they look sometimes. It's interesting to try to erase this way. And so now if we go back to this original limit that we're trying to figure out, what do we do? So the nicest limits are when we were able to evaluate by direct substitution, where you have the limit as x goes to 5 of something, and you just plug in the 5 and see what you get. But we can never really do that ideally when we have infinity. So, for example, the feeling here that we did where you could plug in an infinity to get an answer, you really don't want to think about it that way, because arithmetic just doesn't work with infinities. Sometimes it may see a simple way to get that answer, as we did where kind of like 1 over infinity equals 0. But anytime there's a balancing act going on, like a quotient or something like that, like an infinity over infinity, then that logic immediately goes away because infinity is not a number, so it can't cancel itself out or things like that. So what are our other ways to consider something like this? Now they have numerically, graphically, analytically, or algebraically are all possibilities. So here's one way I might help make this easier for us to see. We could rewrite this as a limit as n tends to infinity of 2/3 to the n, using the property of exponents, that if you have the same exponent in the top and the bottom, then you can pull that out of the fraction, basically. And if you raise 2/3 to higher and higher powers, you'll get the numbers that we were observing over here, going down this list. So the book spends some time, which it's a little harder for me to do, but I'll try it a little bit in this case, doing this graphically. So let's see. You can sort of see these are discrete values. You can try to see what those discrete values might be. So if I try to sort of draw this line, let's make that black. So this might relate back to what we were just doing last chapter with like considering functions as they go off to infinity. But in this case, we only have whole number values, right? So I have basically 1 here, 2, 3, 4. And this is, the sequence is not a continuous function. So if I put my scale up here where this is at a 1, then my first value was at 2/3, should be like about here. Then my second value, 4/9, is a little less than half, so that would be like there. 8/27, well, 9/27 is 1/3, so 8/27 is a little less than a third. Here. So 16/81, 20/81 is over 80 is 1/4, so that's less than 1/4. So this is not a continuous function, but you can still kind of try to see the pattern that you're getting. And what you might observe is that if I were to fill in that pattern, what I have here is the function 2/3 to the x power. And what happened is that with that continuous function, I just chose to only plug in whole powers of 2/3. But this is an exponential function where the base is less than 1. And you may just know that the end behavior of exponential functions like this is that this is an example of exponential decay, and that the limit of this is 0. So that would then tell me that the limit that we have here in our original problem is going to come out to be 0. Questions, comments, discussions about that?
Professor, so you solved this graphically, right? But if we were to just look at the sequence itself, could we also conclude from there that since the numbers are getting smaller and smaller and smaller, it tends to 0?
Well, it's a little harder because the graphical interpretation allowed me to recognize that these are specific selected values from a continuous function that I already know the end behavior of. And the reason I say that is if you're looking at the numbers 2/3, 4/9, 8/27, 16/81, what if the limiting value was, I don't know, 3/1000ths? What if it was a little number, so they're heading down toward that number, but they're not heading down towards 0, right? How do you know that? That's the challenging part. The numerical approach to understanding what's going on is helpful. It gives you a sense of its reality, but it doesn't necessarily help provide an answer in a concrete way.
I see.
And if you're producing the values of your sequence far enough down the line, like putting in a 10, putting in 100, putting in 1,000, it's kind of like just looking what points on the graph would be farther down in the line. And that's kind of a graphical. Like graphical and numerical are very, very similar to each other because the graph is just the picture of the numbers that you're figuring out, right? So yeah, it's not as concrete as you would like. There isn't a straightforward procedure here. That's the nature of the challenge of calculus, is that we have to think about things in different ways. But, that's what chapter 2 and limits were all about. And it's definitely good for us to go back to these core concepts that all of calculus is based on. And we're going to basically be doing this throughout chapter 8 and 9. It might be that some folks want to go back and review a bit of chapter 2 stuff. Maybe that'll be helpful. Maybe not. I don't know. We're just doing it in context. But we definitely want to be in a position where we could, for example, evaluate the limit as n goes to infinity of 2/3 to the n, or something like this, somehow. Probably going through examples that are specific is our best way to do that. So let's consider, We did the one that they gave us, then they did the one that I made up. And the reason I made this one up is to show the danger of just trying to think of like infinity over infinity and then do arithmetic with infinities. And to remind us that in limits that when you have an indeterminate form, that becomes problematic. So let's look at another example. Let's try to see example, what is this? 4, which is on page 599. And let's, okay, let's look at a couple of these as time permits. So in A, they give us a sequence by using set notation. We have -1 to the n divided by n squared plus 1. And then they point out by using that limiting notation that n begins at a 1 and goes off to infinity. So this is an infinite sequence. So they give us this, and then the task is write the first 4 terms of the sequence and then determine if you believe the sequence converges to try to figure out what that would be, or if you think that it diverges, and then if so, explain why. So first, we want the first 4 terms. So if n is a 1, what do we get here?
-1/2.
Sounds good. And this is similar to one we did before. If n is a 2, what do we get? I think the other one we did before just had an extra n in the top or something.
This is just 1/5.
And if it's a 2, it would be a +1, right?
Yes, positive 1/5. Yeah.
And then if n is a 3?
-1/10.
-1/10, and it's said to do 4, right? Yeah. So what's if n is 4? What do you get?
Be positive 1/17.
And then ... So those are the first 4 terms. So we're able to do that just by plugging into the formula. So then the follow-up question was, if you believe the sequence converges, make a conjecture about its limit. If the sequence appears to diverge, explain why. So that's basically asking us if this is a sub n, then we want to figure out the limit as n tends to infinity of a sub n. And it's either a number, because it converges to a value, or we say it diverges or the limit doesn't exist.
So just as a general observation, could I notice that it's -1/2, positive 1/5, -1/10? Would that make it diverge?
So you're noticing that the signs oscillate, is that right?
Yes.
Very good. So definitely the signs oscillate, and the problem in this case is that it's hard to put a specific function there.
Limit is kıramış.
The limit is what? Didn't quite follow that.
Şayet 0 باشه, 1 divided by a big number.
1 divided by a big number, something like that, right? Okay, so there was a couple comments there. We could, again, look at this graphically, numerically, analytically. So basically, on the top, you have a positive or a -1, as was commented on and observed. And on the bottom, you have a number that's just getting bigger and bigger and bigger and bigger and bigger. So let's do this. So I'm not going to try to specifically graph those nice values, but I'm just going to try to quickly graph a suggestion of what that would look like. So the number is getting bigger and bigger on the bottom, and the top is switching between a 1 and a -1. So I have like a -1/2, maybe here. Then I have a +1/5, then a -1/10, and a positive 1 over 17. So they are oscillating in value, but they are also getting smaller and smaller in size. So even though they're bouncing up and down above and below the x-axis, the values themselves do seem to be settling in on 0 because they keep getting closer and closer to 0. Does that make sense?
Yeah, that makes sense.
So here's how they describe it, because this is a solution in the book, because really there's not anything you do here other than draw this conclusion analytically by understanding what a limit is. It says the terms decrease in magnitude and approach 0 with alternating signs. The limit appears to be 0, and then they refer to figure 8.3, where they graph the points much better than I did. 8.3 on page 599. Okay, so that's their example for A. So now let's try for B. In which they give us the sequence of A sub n is equal to, and they have cosine of n times pi. And again, this is starting with the first term, so n equals 1 to infinity. So this is an infinite sequence. And so we are first tasked to determine the first 4 terms of the sequence. So if n is a 1, you get cosine pi. What's cosine pi again?
One?
I think it's a negative 1.
1/2, something like that.
So cosine starts up here, goes down, goes up like that, right? So when you're at pi, I think you're down at the bottom of the bump. So I think we start with a negative 1. How do you guys feel about that? So then when when n is a 2, then we have the cosine of 2 pi, which is at the top of the bump, which is a positive 1. And then if I go to 3 pi, you've moved down to the bottom of the next bump, a negative 1. And then if I go to 4 pi for the 4th term, that's 2 periods in, I'm back up to a positive 1. And I'm putting the dot, 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 because they said to determine the first 4 terms. How do you guys feel about that? Questions, comments, discussions? All right, so take note. They gave us a formula for the sequence terms as a function, but recognize that we're normally used to dealing with cosine and sine and imagining a continuous function with all the intermediary values and a smooth curve. But a sequence is just just numbers. It's just a list of values. So the sequence in this case is just negative 1, 1, negative 1, 1, just alternating between a negative 1 and a 1. So for example, even though they gave us this with this formula, this would be exactly the same as the sequence if I just had negative 1 to the n. So we have to recognize that there's sort of a weird, challenging equivalency here that we may not be used to. You're used to seeing every functional presentation as like a formula that you can graph. Well, now our graphs are just these points. They're just individual values. And there may even be different ways to obtain that list of values than the one that we were given. Clearly, cosine of n times x is not the same function, but -1 to the n is a formula that would produce the exact same values. All right, so then finally we were tasked to figure out if we felt that this converged to a value or not. So we would want to consider the limit as n tends to infinity of cosine of nx, or I'm sorry, n pi. Thoughts about that? Questions, comments, or discussion?
It would diverge.
Diverge. And so again, what's the sense of coming to that conclusion?
So since it's oscillating continuously between -1 and 1, it doesn't settle on a single value, so we can conclude that it diverges.
Yeah, that's good. It boils back down to the basic concept of a limit. The limit exists if, in this case, as n gets bigger and bigger and bigger, the resulting values get infinitely close to a single number. And so if you just keep going back and forth between 1 and -1, that sequence will basically never settle on a value. It'll never settle into a particular number. The previous ones, since they just got smaller and smaller and smaller, they got infinitely close to 0 as time went on. Whereas this gets infinitely close to no specific value because it just keeps bouncing back and forth. So we would say diverge, basically. Because the limit does not exist, it's a divergent sequence. And that would be true if it, even if it went to infinity, we would still say it diverges. Let's do one more example. So, and this will also be a little reminder maybe of some of our previous stuff. This is page 599 still. So we're going to have a limit of a sequence. So they give us, we'll just look at A. No, sorry, A sub n. A sub n is equal to 4 n to the third divided by n to the third plus 1. It says, enumerate and graph the terms of the following sequence and make a conjecture about its limit. So we're just going to go right to the conjecture part instead of trying to graph this, meaning we're trying to evaluate the limit as n tends to infinity of 4n cubed divided by n cubed plus 3 or plus 1. So how do you guys feel about your limit evaluating skills on a problem like this? So we did quite a few problems like this in chapter 2. And so you can do this again, graphically, numerically, algebraically. Since they say they want you to enumerate and graph the terms, they're focusing on you looking at this numerically and graphically. And really, sometimes that's our only choice. But of course, I kind of can't help but remind us that we actually had a way to do this back in chapter 2. And the way was to first simplify it algebraically. You may also recall a process similar to this when trying to determine the end behavior of rational functions. But basically, I can multiply or divide out the top and the bottom by the highest power of these polynomials. So I could basically multiply the top and the bottom by 1 over n cubed. And that would allow me to simplify this algebraically so that this is the limit as n tends to infinity. And when I distribute this, n cubed times 1 over n cubed, those cancel, giving me a 1. And here I would distribute on the bottom. And so on the top, I get 4 times 1, which is 4. And on the bottom, I get 1 over n cubed times n cubed, which is 1. And 1 over n cubed times 1, which is 1 over n cubed. So algebraically, the original expression is equivalent to this one. And in this one, the only part of this that has an n in it here, this part, we've already looked at. As n goes to infinity, 1 over n to a power, like n cubed, that's going to go to 0. So since this part goes to 0, you're just left with 4 over 1. So we conclude that this limit is 4. Questions, comments, discussions about that? So in the book, they do.
Sorry, I had a question.
Yeah, go ahead.
Could we potentially use L'Hopital's rule for this as well?
You may, yes, absolutely. So here's the rub, okay? And we're going to look at this a little bit more in detail in 8.2. So maybe after a little break today, we'll try to get to that part. But L'Hopital's rule gives us a way to evaluate limits like this because it's in that indeterminate format where it's an infinity over infinity, and then you can take the derivative of the top and the bottom. But all of that applied to continuous functions. This is not a continuous function because we're only doing this for discrete values of n. N can only be a 1, a 2, a 3. If we make the graph, right, we get this, and they do a graph for you in the book, but the kind of thing we get is we get these points, these individual discrete values. We don't have a continuous function. And for example, the derivative doesn't even make sense. So we'd like to basically treat it as if it was a continuous function when evaluating the limit. And the first theorem of chapter 8 actually shows up in 8.2, which basically tells us that if this were a continuous function that had a limit, then the limit of this sequence will be the same as the limit of that function. So basically that means when it makes sense to do it, you can, and if it doesn't make sense, you can't. So I would just point out to you, for example, in what we had above, if I have -1 to the power n, I can plug in powers of n and I can see what I get. I'm going to get a 1 or a -1 when n is a positive whole number, like 1, 2, 3, 4, 5, 6. But if I have -1 to the function x, these are not the same thing. Obviously, you would get the same value when for x you plug in a nice whole number like for n, like 1, 2, 3, 4, 5. But when you put an x there, that's a continuous function, or it wants to be, and that suggests you can plug in whatever you want. And my problem is if I plug in a 1/2, for example, I get square root of -1, which isn't a real number. So we've never really worked with things like this where you had a power on a negative because of the fact that that only works for nice whole values of x. It doesn't work for regular values of x. And if it's not a continuous function, then you can't take the derivative. You can't do a whole bunch of stuff we've done before. So ultimately, it gets a little bit more confusing. That's why they hold off on having this discussion more deeply until a little later. And that we are looking at evaluating a limit, but that's why they're sort of limiting your view of this as to numerically and graphically, because we can't use our limit tools yet from chapter 2 because they only apply to functions that were continuous at the limiting value. They didn't apply to these discrete 1 point at a time sequences. I don't know if that helps answer your question, but how do you feel about that?
I kind of understand the reasoning.
Yeah, so it's good to think about how do we evaluate limits, what are our tools from before, but we can't just do everything we did before. You're gonna have to consider each problem as its own circumstance and whether it makes sense to do it in that case, okay? And we'll just have to get in the details to that as we proceed into the chapter. Okay, so now these are all sequences. So the last thing I want to do, and then we'll take a little break after that, is to give an overview, still in 8.1, of a series. So any questions about what we just did on all of these writings before I erase it? So this was about sequences and the limit of sequences. I guess that's what it primarily was, starting from the top. Limit of a sequence, terms of a sequence, notation for a sequence. Any questions about that before we move on to a series?
Is the limit always into the infinity?
Well, we did several different limits here, right? So this limit, when a sub n was 1 over 2 to the n, that limit turned out to be 0. Then the limit of this one here also turned out to be 0. But when we got down to the cosine thing, it was divergent and there was no limit. And the limit of this one was 4. So the limit will vary from problem to problem. It will either converge to a specific value like 0 or 4. But if it doesn't converge to a specific number value, then we say it diverges. Does that answer your question?
Oh, yeah.
Yeah. Other questions or comments on what we've been looking at so far before we talk about series? Okay, let me clear this. All right, so just a basic idea for those who aren't used to the term. We've discussed having members or numbers of a sequence. The series is what you get when you add those sequence values up. So the standard notation for series is S sub n, basically meaning that you are adding up. So let's say this is the sum of a sub n. So a sub n is a list of numbers, and so S sub n is the series of a sub n. It's the sum of those values. So for example, I could have a sub n equal to 1, 3, 7, 11. So as I described before, actually I put this in a box if I'm going to do that. In this case, this is a finite sequence. So if I wanted to see what series that led to, then I would do the summation as n goes from 1 to 4, or I or k, of a sub n, which would be equal to 1 plus 3 plus 7 plus 11. which is 22. So I have a finite sequence, and if I take the series for that finite sequence, I would just add up those finite numbers and get an answer. So a series, when the sequence is finite, or a finite series, is just a sum of a finite collection of values. You add them up and you see what you get. So there isn't too much mystery there, even though later when we talk about these in 8.3, we'll talk about formulaic ways to calculate sums of finite series when there's a formula or it's kind of challenging. But at this overview, we're instead going to focus on the idea of when we have an infinite sequence, which leads to an infinite series. So let's say instead that we had a sub n equal to, how about 2 to the n? So just to try to visualize that, this is, the first term is 2, the next term is 4, the next term is 8, etc. So then I could sort of say, what is the summation in order to get a series? I'm going to use an I just to remind us that we can have different indexing scripts here, from 1 to infinity of 2 to the I. And that you could imagine this is 2 plus 4 plus 8 plus 16, etc. Okay, so this would be a summation, and we would try to basically imagine continuing this process and going out as far as you can. So what do you think happens if we just keep adding numbers that are getting bigger and bigger and bigger and bigger? What kind of a sum are we headed toward?
Positive infinity?
Positive infinity. So we could think of this almost like an idea where we could say, yeah, it just keeps getting bigger and bigger and bigger and bigger, so that's going to go to positive infinity. But how would we approach this systematically, and how could we draw a conclusion like that? We have to think about notations. So we're going to introduce the idea of partial sums. I think I'm supposed to listen to there somewhere. So somebody, could you please mute your mic because we're hearing background noise. So what is a partial sum? It's going to give us a way to talk and think about this idea of adding an infinite list of numbers that just keep going on and on and on and trying to draw a conclusion. So a partial sum, which we could write as S sub I or S sub n or any index we want, but let's use an I since I'm using an indexing variable here, will be the sum of the first I terms. So let's say you had this list of things to add and you were going to add those up yourself. The basic idea is you would go left to right and just start adding, and then you'd keep a running total as you were going, and then add the next thing along. So if I'm adding up this list, I'd say, 2 plus 4 is 6. That's what I have when I do the first 2. Then I add 8 to the 6 to get 14. Then I add 14 to 16 to get 30. And so you would keep a running total along the way to try to see where this total was going. And so that running total is what the partial sum is. So for example, S sub 1 would be just the first term 2. Oops. S sub 2 would be the sum of the first 2 terms. So that would be 2 plus 4, which would be 6. S sub 3 would be the sum of the first 3 terms, 2 plus 4 plus 8. But if you take note, you already added the first 2 terms together before when you got the 6. So I can recognize that S sub 3 is the total that you got when you did S sub 2 plus the third term, A sub 3. In this case, that's 14. So that we can create partial sums by adding up the first I number of terms, however that may be. Oops. So if we do that, then we end up taking the limit as n tends to infinity of S sub n. So the partial sums create a sequence of numbers. So what were the numbers? 2, then 6, then 14, then 30, right? This is S sub 1, S sub 2, S sub 3, S sub 4, and that just goes down and down and down. So the partial sums are basically what you would be getting if you were keeping a running total as you were adding up the terms of the sequence. And you look at that running total and see if it has a limit. And as was suggested in this case, we would get a positive infinity. But if it doesn't settle in on a number, we would say that S sub n diverges. It basically diverges to infinity.
So the last example that concluded that the, not the series, but the sequence led to 4. Would the sum of that series then lead to an actual number?
Well, last time the terms were getting closer and closer to 4, correct?
Right.
Well, let's say you adding all those numbers up. If I'm adding up a bunch of numbers that are all close to 4, it's basically like I'm adding up a bunch of 4s, which would diverge.
Okay.
So that's why I'm trying to use this. It's hard. I'm trying to use this notation to have us think about the difference between the limit of the sequence numbers themselves and the limit of the partial sums of their values. So compare the S sub 1, S sub 2, S sub 3 here with the A values, right? So here are the A sub n values, 2, 4, 8, 16. So the A sub n values are not the same as the partial sums, because the partial sums are keeping a running total of those A sub n values. In this case, the A sub n's have a limiting value heading off toward infinity, and the partial sums therefore also have a limiting value heading off toward infinity. But for example, in the example that you just were indicating, we could say, what if, let's just use a constant. What if A sub n was equal to 4? So what does that sequence look like? 4, 4, 4, forever. It's a constant sequence. But then what would the partial sums look like? The partial sums, the first one would be 4, then the next one is 4 plus 4 is 8, and the next one is 4 plus 4 plus 4, which is 12, 16, So in this case, the limit as n tends to infinity of a sub n is 4. But the limit as n tends to infinity of s sub n is infinite, so it diverges. What do you guys think about that? So it's quite possible that the sequenced numbers have a limiting value, but when you try to add all of those up, you don't approach a limit, you instead approach infinity, for example, so that it's divergent. Okay, so now let's consider an example where the series of an infinite sequence, an infinite series, is not divergent. So I think there's a decent one in the book we can use. Let's see if I see it here. Yeah, let's look at example 7 on page 601. So it says, consider the infinite series. And instead of giving it with a notation, it just writes them out. So we've written out a sequence of values, but we've put plus signs between all of them, which means we're adding up all the terms of the sequence. That produces a series. And because the numbers go on forever, this is an example of an infinite series. So it says in part A, to find the sum of the first 1, 2, 3, and 4 terms of the series. So I'm going to say it says to find the first 4 partial sums. And then B, what value would you assign to the infinite series? Questions about the presentation of the problem?
Is that a V or an R?
What-
Fine.
Oh, sorry. Let's see here. You're talking about this thing?
Yeah.
That was an infinity.
Oh, okay.
There we go. Find the infinite series value. They described it as what value would you assign to the infinite series, and then they listed it again, and I didn't want to write all of that in my scribbly notation here. So find the infinite series. So this thing up here, what would you get? That's the goal. So again, even though this is example 7, we're just doing our first examples of series, so they're trying to make it hopefully be not too complicated of a result, even though our real goal here is to understand what we're talking about and the language and how to annotate it and things like that. So the first thing I would use is my partial series notation for the first 4 partial sums, my partial sum notation. So for example, the first one would be S sub 1. And that's where you just take the very first number in the sequence. So that's 0.9. Because there's nothing else to add it to. S sub 2 would be the sum of the first 2 terms. So I would be adding this one and this one. So that gives me 0.99. S sub 3, 0.99. And on the third term, I add a 9 in the third decimal position, so I'd get a third 9. And similarly, finally, in S sub 4, you get 4 9s after the decimal. Questions about part A? So in part B, it says, what value would you assign to the infinite series of 0.9 plus 0.09, etc.? What value would you find for this infinite series? So we could use the language to say that this is the summation. Well, let's not do that. The better way to say that is that this is the limit as n tends to infinity of the partial sums S sub n. So the way you evaluate an infinite series is you take the limit of the sequence of partial sums. Not the sequence of the terms themselves that were added, but the summing value that you would get along the way if you continue to keep adding those and adding another number. So, suggestions? Thoughts? Is that something we can evaluate?
Yeah, would it be 1?
Absolutely. So basically, you just keep adding another 9. You could, it goes back to an equivalency which you may or may not have discussed in first semester calculus, that if you have 0 with a repeating decimal of a 9 that repeats forever, that's equivalent to 1. And so that's what we get if we just keep adding on another 9 in a further and further position. Questions, comments, discussions about this example 7 from the book?
Could I just draw a little bit of a conclusion in that if we go back to the sequence of cosine sub n of pi, and it was from n equals 1 to infinity, -1, -1, -1, -1, -1, so on and so forth.
Yes.
We know that the sequence diverges, but if you do the limit of the series, then it winds up being 0.
That's a great example to consider. I appreciate your bringing that up. The way to consider it formally is to write out a list like we just did here of partial sums and ask yourself if that list of partial sums converges. So let's say we can write some of this down here. Maybe I'll just change colors so that it seems like a side example. So here's your sequence, right? A sub n, and I'm going to use the simpler formula, -1 to the n, which gives you -1, 1, -1, 1. You can arrive at those using a cosine, or you can just say, I have -1s and 1s alternating, right? Okay, so what would the sequence of partial sums be? So what's the first number in the partial sum?
-1.
And the next number?
Be +1.
Nope, that's the next number.
Oh, right, I'm sorry. It would be 0.
Right, and that's why you're seeing a 0, because you see these things adding up and canceling out, right?
Right.
So what would be the third term in the partial sums?
-1.
And the fourth term?
0.
And that's what keeps going. Does that settle in on a value?
No, I guess that still diverges.
That's right.
Oh, how bizarre. Okay.
Yes, that's right. So this is the perfect example, and so I'm so glad you brought that up, to recognize why we have to think about it with these partial sums. the basic way to think of it is that if you keep tacking on a 1 and then a -1 and then a 1 and then a -1, there's no way that the sum that you get can stabilize on a value. It keeps bouncing back and forth the same way the original sequence did. Does that make sense?
Yes, that makes sense. So
Yeah.
just absolutely.
In that case, that would be a divergent series. Whoops, thought it was an eraser. There we go. See how much of that I got. Okay, so so let's take note here, and I have a follow-up question. So if these terms,
Sorry.
oh, go ahead.
Question. Just so I see if I understood what was just said
Yes.
from before. If we're doing a sequence, it diverges, but if we're doing a series, it converges to 1.
So which one are you talking about? You mean the -1 +1 thing, or do you mean the one we're looking at now with the decimals of 9s?
The -1.
Okay, so the sequence also diverged. It did not converge because it
Not
kept
converge.
bouncing back and forth between a 1 and a -1,
Mhm.
never settled on a value. So in that case, and I'll write it here, the limit as n tends to infinity of -1 to the n, if that's my sequence, diverges.
Right.
And then if that's my sequence, then I could take the limit as n tends to infinity for the series of the summation as I goes from 1 to n of -1 to the I. So the notation may be overwhelming here and may not be helpful, but this is how we would write the two conclusions that we just drew. So in this first example here, I have a sequence, -1, 1, -1, 1, -1, and I can take the limit of that sequence and see as n goes to infinity if that settles in on a number, but it doesn't. So I say that diverges.
Right.
Then in the second one, I can take that exact same sequence of numbers, and then as I'm going -1, 1, -1, 1, I can add those up along the way, and I can take the summation as I goes from 1 to n of those. Well, when n is a 1, I get s sub 1. When n is a 2, I get s sub 2. When n is a 3, I get s sub 3, because these are partial sums, and I can take the limit of those partial sums as n goes to infinity. But in this case, this doesn't exist either, because this summation just keeps changing between a -1 and a 0 and a -1 and a 0 and bounces back and forth, so it also diverges.
Okay, I see.
Yeah, challenging to wrap our minds around this, but you guys are doing great questions to try to help with this. So close. All right, so I have a follow-up question here. So in this example we're looking at here, we have these terms here. So I'm going to say we're going to let these terms be a sub n's. So these are our sequence. This is a sub 1, this is a sub 2, this is a sub 3. So that we can formalize this a little bit. Yeah. So then, first of all, I'm going to try to have, so then the sequence of a sub n's is the sequence of 0.9, 0.099, 0.009, etc. So then in the infinite series, we added these up and we drew a conclusion that we get 0.999999, which is the equivalent to 1. So consider the limit as n tends to infinity of a sub n. So what I'm asking for us to think about now is what is the limiting value of the sequence numbers themselves, not after you add them up, but before you add them up. What are the terms themselves approaching? What do you guys think?
Is it 0?
Absolutely. So we have a situation where the values themselves were approaching 0, but when we added them up and took the limit as n went to infinity of the partial sums of those numbers, we got 1. So this is kind of like the discussion we had in class about whether an improper integral could converge or not. Remember when we were looking at those Gabriel's horn, tails, and those kind of area problems? We basically said that as that little slices of area that you're adding up under the curve goes off to infinity, they can converge on a value if they're just getting smaller and smaller and smaller. Then as you add more and more, it doesn't disturb your total. The same thing goes on here. In order for the series to converge, the terms of the sequence that's being totaled up must be going to 0. If your sequence, like we looked at before, has a stable value of like 4, well, then when you add all of those up, because you keep adding more 4s, that's going to go off to infinity and diverge. If, as we were just discussing in the example with the oscillating 1s and -1s, if your terms of your sequence, even if they don't stay constant, if they're going back and forth between some non-zero number like a 1 and a -1, well, then when you add those up, you're still never going to settle in on a value. The only way you can settle in on a value is if the terms that you're adding on every time are shrinking away to nothing, if they're heading towards 0. So you need the limit of the sequence terms to be 0 in order to have a chance for the series to converge to a value, to settle in on a value. That's not a guarantee, and we'll discuss this more later, but it sort of sets up the dynamic that you want to think about. I'm looking at what happens to the terms themselves. If the terms themselves are not shrinking away to 0, then there's no way I add them up infinitely that I'm going to get 0, that I'm going to get a number. I'm going to get a set value. But if they do shrink away to 0, as in this example, then there's a possibility that when I add all of those up, they get a set value, like a 1. And the two examples we did with improper integrals was we did the integral from 1 to infinity of 1 over x dx, and the integral from 1 to infinity of 1 over x squared dx. And you may recall that this one went off to infinity, so it diverged, and this one became a 1. So these were area problems, but they kind of have the same dynamic going on as individual values. If the individual values are not going to 0, there's no way that an infinite collection of them could ever add up to a finite number, that it could ever settle on a value. And if they do go to 0, then it's possible that you can get a finite infinite series value, but it's also possible that you don't. It's possible that they go to 0, but they don't settle in on a value, or that they go to 0 and that they do settle in on a value. That both of those are possible. And you'll see this through examples, but you want to try to paint a big picture in your mind that this is what's going on. Okay, so more than enough. We're already almost 2 hours in. We have about another 42, 41 minutes, something like that. So I'm going to take a 10-minute break, and then we'll just let you guys go to the restroom, clear your heads, and then we'll just try to do a little introduction to the 8.2 a little bit, just to see where we can get to. 8.1 is pretty long and challenging. So let's come back at 2:45, and then we'll pick up in 8.2.